morning all. Today we are going to discuss about the scattering parameter. Last class we have discussed the impedance parameter, admittance parameter, ABCD parameter that is left. We will deal with that. Even hybrid parameter is also left. But anyhow, we have a brief idea on the impedance matrix and the admittance matrix for a given network. Now today we are going to discuss about the scattering parameter. Okay, scattering parameter, how it is going to help us while we are dealing with the microwave networks. Okay, now the demerit of those impedance parameter, admittance parameter, hybrid parameter and the transmission parameter is that it can't work in the higher frequency range. That reason also we have discussed in the last class. So the thing we should consider that the length of the device must be greater than lambda. If the length of the device is very greater than lambda, that means we are working on the high frequency range. Now once if it is operating at a high frequency range, that means we will deal with respect to the microwave frequency, and we will deal with respect to the scattering parameter. Okay, let us consider this is a device, and here I have identified some source, that is Vg, okay, having internal impedance Zg, and its incident potential is A1, reflected is B1. Similarly at the port 2, incident is A2 and reflected is B2. So this is with respect to the load, this is with respect to the incidence. Now when we are giving the power from incident from port 1 to port 2, that means Pi we are going to identify, input power. This is the first. Done. Due to the input power means due to the incident potential, we are going to calculate the incident power. Similarly, reflected power is going to be calculated with respect to the reflected potential, that is at port 1 with the help of B1, that we will discuss. And how much information we are going to deliver at the load is nothing but the difference between input power minus reflected power. That I can say it is called transmission power. So power transmitted. So power, when it will transmit, incident power subtracted with the reflected power. Now if it is subtracted with reflected power, then the total power we are going to deliver at the load. And if the load is having only impedance, that means no input power from the load, so that means power available will be with respect to B2. That also we will discuss now. Okay, so first let me write the input power. So it is a two-port network. For nth port network, if I want to discuss with input power, so input power will be half of AN A square. So that means AN is the normalized component, normalized potential, or you can say it is a normalized. We will discuss what is AN, but for the timing AN is the input power. Okay. Similarly, the reflected power I can write half of mod Bn square. Half Bn square means it depends upon the reflected potential for nth port. So here I have represented the reflected potential as B1 and incident potential is A1. So this is mod V square you can consider, but it is called as a normalized component. Okay. So this AN and BN are the AN and BN are the normalized incident and reflected potential. Okay, reflected wave amplitude for nth port. Okay, so this is the two powers through which we can determine what is the output power. Now what will be my output power if there is no source is available here? Output power is nothing but input power minus reflected power. So that we will see as, so if I will write what is the power transmitted for the nth port, I will write incident power minus reflected power, that is half of an mod an square minus mod bn square. So this is the transmitted power we are going to identify. But now let us consider this is for nth port. Now let us consider if it is a two port network, that means how many parameters we are going to identify. If it is a two port network, if we are considering two port network, two port, so that means how many parameters should be there? 4 parameters, because 2 cross 2 dimension of matrix we have to generate. So 4 parameters here. Now if it is working in this particular condition, length is very greater than your wavelength, that means we are entering to the microwave frequency, higher range of frequency. So when we are entering to the higher range of frequency, we will write all those parameters in terms of scattering parameter. Okay, so that scattering parameter I can write S11, S12, S21 and S22. So these are the scattering parameter, and each scattering parameter is having its unique identification that I will discuss now. But for the time being, if it is a two port network operating at a higher frequency range, you have to represent your scattering parameter with S, and how many number of parameters? 4 number of parameters. If it is a 3 port network, 9 number of parameter. If it is a 4 port network, 16 number of parameter. So like that we have to analyze it, and each parameter is having its unique identification that we will discuss now. But for the time being, if it is a two port network, let us consider this figure. It is having the two port. Port 1, incident potential is A1, reflected potential is B1. For port 2, incident potential is A2 and reflected potential is B2. So what is this A2 and A1 and B1 that we are going to write? So A1, this is A2, B1 and B2. So normalized potential for A1, it is Vi1 divided by root over of Z0. Okay, but what is Vi1? Vi1 is V1 minus V reflected 1 divided by root over of Z0. As I have told, it is a normalized component, so that means you have to divide root over of Z0. This is the standard relations. Okay, so this is for A1. Similarly, A2 incident, so it is Vi2 divided by root over of Z0. But what is Vi2? Vi2 is V2 minus V reflected of 2 divided by root over of Z0. But what is V1 and all? Let me write that. So V1 is equals to Vi1 plus VR1, because it is the total potential. If I will add incident potential with reflected potential, I will get V1, means potential available at port 1 here, and V2 is equals to Vi2 plus VR2, so reflected potential at port 2. So here I have written Vi1 is equals to V1 minus reflected potential divided by root over of Z0. Similarly, A2 is Vi2 divided by root over of Z0, which is equals to V2 minus VR2 and root over of Z0. Now this similarly, what is B1? B1 is the reflected one at the port 1. So what I will write? VR1 divided by root over of Z0, or V1 Vi1 divided by root over of Z0, because VR1 is equals to V1 minus Vi1, you can write. Similarly, what is B2? B2 is VR2 divided by root over of Z0, or V2 VI2 divided by root over of Z0. So these are the incident potential and incident reflected potential at port 1 and port 2 in normalized form. Okay, in normalized form. Now with the help of these, we are going to identify the parameters S11, S12, S21 and S22. Okay. And as you can see, the total power transmitted will be the incident power minus reflected power at this particular port. Either you can identify for the port 1 or either you can identify for the port 2. Only the thing is you have to substitute this n value as 1 for port 1 and n value as 2 for port 2. Okay. Now, so these are the normalized potential. Now we will form a relation between this normalized potential with the incident with respect to reflected with our scattering parameter. Okay. So let me write that. So in normalization process, we have to consider characteristics impedance for that network is 1. So first is B1 is equals to S11 A1 S12 A2 and B2 is equals to S21 A1 and S22 A2. This is equation 1 and this is equation 2. Here what we are going to relate, it indicates that the reflected potential is related with respect to the incident potential in order to determine the scattering parameter. Okay, and this thing I can write in the form of matrix, that is B1 B2 with a matrix of S11 S12 S21 and S22 with incident potential, normalized potential at 1 and 2. If you resolve this, you will get two sort of equation, and this S11, S21, S22 and S12 all are called as a scattering parameter. Here power is going to be scattered. Okay, so that word is called as a scattering. So power is scattering into two number of ports. So here it is only one port, because from one port to one port is available. Similarly, there are n number of ports are there, and power will be scattered throughout the ports. Some power will be less, some power will be more. So according to that we have to analyze. So here it is called as a normalized form. So in order to determine S11, so what we have to make similar to the Z impedance and Y impedance, here we have to make A2 as 0, so that we can determine this S11 and S21. Similarly, if you make A1 and A1 as 0, you will get S12 and S22. Okay, so let me write those equations. So first S11. S11 means it is B1 by A1 at A2 is equals to 0. Now what is B1? B1 is nothing but a reflected potential at port 1. And what is A1? It is incident potential at port 1. So reflected by incident, what is that? It is called as a reflection coefficient. So this is called as reflection coefficient at port 1. Okay, because reflected by incident potential, if you substitute, you will get a reflection coefficient. So that reflection coefficient is called as a S11. Always remember that when we are forming this scattering matrix, this diagonal element S11 and S22, these all are called as a reflection coefficient. If it is more than two number of port, then also the diagonal elements S11, S22, S33, S44, S55, SNN, all are called as our reflection coefficient. Remember that. Okay. So here S11 and S22, these two are reflection coefficient at port 1 and port 2. Next, S21 is equals to, it is a ratio of B2 by A1 at A2S0. Now what is B2? B2 is the reflected potential, normalized potential at port 2, and what is A1? It is the incident potential. Now if I am going to take a ratio of the reflected potential with respect to the incident potential for port 2 and 1, it becomes as an attenuation. It will contribute the attenuation factor. It will reduce the information. Okay. So this particular ratio is called as a attenuation of wave. This is called as attenuation of wave while power is flowing. While power flow, remember this, while power flow. Similarly, with respect to these two, now we are going to identify what is S12. So S12 is also, it is B1 by A2 making A1 0. So that means again it is a reflected potential of port 1 and the incident potential of the port 2. So that means it will contribute the attenuation, because these two are different. Different means not with respect to the port 1, not with respect to port 2, but it is a transfer function. Okay, transfer relation with port 1 and port 2. So here this is also called as same. I will write do. So it is an attenuation of wave while power flow from a particular port. Okay, so this is also attenuation factor, this is also attenuation factor. Now we have left with S22. So what is S22? S22 is B2 by A2 and A1 is 0. Now what is B2 and A2? B2 is reflected potential, and what is A2? It is the incident potential in which particular port? In the second port. So in the second port, if you take a relation of reflected with respect to incident, you will get the reflection coefficient. So this is called as reflection coefficient. Reflection coefficient in which port? In port 2. Okay. So this is one relation. This is one relation. This is one relation, and this is one relation. So always remember that in scattering matrix, the diagonal elements, all diagonal elements, whether it is a 4-port network, whether it is a 5-port network, whether it is a 6-port network, or even it is a 2-port network, the diagonal elements are indicating as a reflection coefficient of that network for individual port. If I will write S11, that means it is a reflection coefficient for port 1. If I will write S22, that means it is a reflection coefficient for port 2. Okay, and the other combination S12, S21, these all are called as attenuation. This attenuation means it will suppress, means whatever the information we are going to transmit, it will attenuate the signal, means the signal quality will deteriorate, it will act as a contribution of a noise. Okay, we have to remove this. Okay, so our maximum power must be flow through a particular device. For that, different properties are there. So according to that properties, we can test that this particular network, whether it is a reciprocal network, whether it is a unitary network, whether it is a lossless network, depend upon the properties, we can justify that the given device is a lossless network or a reciprocal network or a phase shifter, or depend upon the nature of the questions. Okay, so this is the basic relation, as you can see. So this is the 2 cross 2 matrix. That means my device is of 2 port. If my device is of 3 port, if it is 3 port network, That means how many elements I am going to identify? It is B1, B2 and B3. Because three port means there will be three incident potential, normalized potential, and three reflected normalized potential. So it is A1, it is A2, it is A3. Okay. S11, S12, S13, S21, S22, S23, S31, S32 and S33. And this diagonal is called as reflection coefficient of that particular network with respect to the individual ports. If it is S11, that means it is a reflection coefficient for port 1. If it is S22, that means it is a reflection coefficient for port 2. If it is S33, that means it is a reflection coefficient for port 3. And other combination S12, S31, S21, S23, S31, S32, all these combinations are called as attenuation. Okay, attenuation of the wave while the power flow. During the power flow, if it is observed any sort of attenuation, and those attenuations are these other factors, and the diagonal element is called as our reflection coefficient with respect to the ports. This is for port 1, this is for port 2, this is for port 3. Okay, so this is the basic representation of a scattering parameter. Next we will discuss that what sort of losses we can identify, because this attenuation means it acts as in losses only. So depend upon this, what sort of losses we are going to measure in this particular microwave network with the help of this scattering parameter. Okay. Okay. So as you can see, there are 4 different losses we are going to discuss now. Okay, these are the 4 losses. For any sort of network we can measure these 4 losses. Okay, let us consider the 2-port network. As I have drawn the 2-port network in which A1 and B1. A1 is the incident normalized potential, B1 is the reflected normalized potential at port 1. Here A2 is the incident normalized potential and B2 is the reflected normalized potential. Okay. Now let us consider this figure. Here it is only having one source and the second port is terminated with a load impedance ZL. So that means no incident power. So whatever the power is going to deliver, it is moving out. So as per the figure you can see that A2 is 0 for that. For this particular case, A2 is 0. But whatever the power is going to be delivered in this ZL, it is due to the presence of this B2. So that is the output power. So output power is going to measure with respect to the B2. So individually I will identify first input power at port 1. Okay. So what is the input power at port 1? So Pi, I will write half mod A1 square. So this is my input power. Done. Next, what is the reflected? Because here incident power is there, reflected power is there for port 1, but port 2 is terminated with a load. There is no source. If there is a source, consider A2, no problem. But if there is no source, that A2 is 0, but B2 will exist. Why? Because the maximum power is delivered in this particular direction, and that reflected sign of this B2 will indicate as a power delivered in the load if there is no input signal. Okay. Next, I will identify the reflected potential. Here all are identifying with respect to the port 1. So what is the reflected potential? So reflected potential is half of B1 square. Done. Next, what is the output power? Output power available at load will be depend upon what? Depend upon this B2, not A2. A2 is the incident power. If there is a source, incident power will be there. But if there is no source, the total power what it is delivering from this end to this end and in the direction of B2. So here I will write the output power is half mod of B2 square. Done. So these are the three basic relations. You have to identify according to the given figure. Here I have terminated that port 2, but in question they will provide one source. So due to that you have to generate A2 as well as you have to represent B2, and then you have to form a relation. Okay, simple. Now in any sort of device we have four different losses. First, insertion loss. Second, transmission loss, or I will say it is called attenuation loss. Then reflection loss, and last one is the return loss. Okay, so we will discuss one by one. Insertion loss means as we are measuring the efficiency. Okay, so if you take 1 by efficiency, the insertion loss you can determine. Efficiency is always measured with respect to output power with respect to the input power for a particular system. Here insertion loss having a general equation 10 log base 10 of input power divided by the output power. Now all are represented in dB, because since we are dealing with the power we need to represent in dB. So it is 10 log base 10 Pi by P naught. So what I will write here? I will write 10 log base 10. What is Pi? Pi is the input power, half mod A1 square. So here I will write mod A1 square. And what is my output power? Output power is half B2 square. Okay, so that mod B2 square. Done. Half will be cancelled out. Now this particular relation I can write as it is 10 log base 10 1 by B2 divided by A1 mod square. I have took this A1 denominator of B2, and what is B2 by A1? It is nothing but S21, because S21 we have identified as B2 by A1 and it is the attenuation factor. Okay, so here I will write it is 10 log base 10 1 by mod of S21 whole square. Then take this square upper side, or if you take this square outside you will get 20 log base 10 1 by S21 mod of S21. Now if it is a reciprocal network, S12 is equals to S21. Okay, so here you can write 20 log base 10 1 divided by mod of S12. Okay, so this is called my insertion loss. Over. So insertion loss simple relation is what? Input by output power. Over. Next, what is our transmission loss? Transmission loss or attenuation loss. So first of all, the ratio will be the power transmitted divided by the output power. So power transmitted is how much? Input power minus reflected power divided by the output power. You will get your attenuation loss. Okay, so here I will substitute 10 log base 10. Input is how much? Mod A1 square. Half I have to common, minus reflected for the port 1 is B1 square. Output is mod B2 square. Okay, now if you take A1 common from the numerator and denominator, what you will get? You will get 10 log base 10 1 minus B1 by A1. What it is? Reflection coefficient S11 square divided by B2 by A1 is what? S21. So mod S21 square. So this will be my relation for the attenuation loss or transmission loss. Okay. Next, what is reflection loss? Reflection loss means incident power divided by the transmitted power. So if you take 10 log base 10 incident power divided by transmitted power. So transmitted power is what? Incident minus reflected. So that will indicate how much reflection losses are going to identify. So here I will write 10 log base 10. So it is mod A1 square, input is A1 square, reflected is B1 square, okay, and half it is cancelled out. Take A1 as common from numerator and denominator. So if you are taking A1 as common, you will get 10 log base 10 1 by 1 minus mod SS1 S11 whole square, because B1 by A1 is S11, which is the reflection coefficient. So this is the relation for my insertion loss, okay. But the thing is that port 1 is excited, port 2 is terminated with a load. So this is the relation for the reflection loss. This is the relation for the attenuation loss. This is the relation for the insertion loss. One more loss is there, that is called return loss. So this I will write here. So return loss is 10 log base 10 incident power by reflected power at port 1, because source is at port 1. If the source is at port 2, then you can take incident power by reflected power for port 2. So there are two return loss we can measure. So it is with respect to port 1. So I will write 10 log base 10 mod A1 square divided by mod B1 square. Half cancelled out. And that too, this A1 take to the denominator. So 10 log base 10 1 by mod B1 divided by A1 mod square. So this I can write 10 log base 10 1 by mod of S11 whole square. Take these two outside, you will get 20 log base 10 1 by S11. So this is called my return loss. Okay, so return loss at port 1. This is all we have measured with respect to the port 1, which is excited with the source, and port 2 is terminated with the load. Similarly, you can measure if port 1 is terminated with a load and port 2 is excited with some sort of source, then all these parameters will going to change. Here input power and output power is with respect to this port 2. Here A2 by B2 will come. So here you will get around S21 and S12. Okay. Similarly, transmission or attenuation loss, incident power minus reflected power by the output power. If you are feeding the power at port 2 and this is terminated, your incident power will be A2, reflected power is B2 and output power is B1. So with respect to that, you can change the parameters, depend upon the situation. Here the situation is providing the power at port 1 and port 2 is terminated. That means no source is available at 2 and we are only delivering the information at port 2. Okay, so according to that I have represented this relation, but it will change as per the given figure. If this source is here and this load is here, all the parameters will change, but the general representation or general equation is this one. Insertion loss 10 log base 10 input by output. General equation, transmission loss 10 log of input minus reflected power divided by the output. Reflection loss, it is input divided by input minus reflection, and return loss input by reflection. So you need to remember all this black term. The red term will change according to the given situations. Okay, so these are the certain losses what we will identify when we will deal with the microwave devices, because this insertion loss, return loss, reflection loss and the transmission loss all are related with respect to the scattering parameters. Okay, as we have represented all these equation in scattering parameter. So next we will discuss now with respect to the properties. Okay, so now we are going to discuss about the properties of S parameter. Basically there are four properties for S parameter. First, the diagonal element, if all are 0, that means by seeing that matrix we can judge that that network is a lossless in network. Okay, lossless in nature. Why I am saying lossless? When we are discussing about the lossless network, the reflection coefficient will come into picture, and if the lossless perfectly matched means ZL is equals to Z0. Now ZL is equals to Z0 means reflection coefficient will be 0. So that means the S parameter, the diagonal element as I have shown, S11, S22, S33, S44 or SNN for nth port, all the diagonal element if it is 0, that means that network is perfectly matched. So that is the first property. So 0 diagonal element for perfectly matched network. For perfectly matched network means ZL is equals to Z0. Okay, load impedance must be equal to Z0, due to which the reflection coefficient will become 0. Now what is the reflection coefficient? As we know, ZL minus Z0, ZL plus Z0. If we put this condition, we will get 0 directly. Now what is the reflection coefficient in S parameter terms? S11 is the reflection coefficient for port 1. S22 is the reflection coefficient for port 2, S33 is the reflection coefficient for port 3, S44 is the reflection coefficient for port 4. If these reflection coefficient are 0, that means the diagonal elements are going to be 0. That is the first property. So 0 diagonal element for the match network. Okay, so reflection coefficient is 0 for the match network. So diagonal elements are the reflection coefficient. So all diagonal elements 0 means it is called as a perfectly matched network. Okay, next, second one, as we have derived the symmetric condition for the S Z parameter. Okay, that Zmn is equals to Znm. So that is the reciprocity theorem. What we have discussed with respect to impedance and admittance. Now we will discuss with respect to the scattering parameter. Okay. For that, symmetric or the S parameter for a reciprocal network. Reciprocal network means S12 is equals to S21. That we have to prove it. But how to prove? It is having a small derivation. With the help of matrix we can analyze it. Okay. So first I have used the impedance matrix converted into the S parameter, because this interrelation, this S parameter and the impedance matrix are quite interrelated with each other. But the thing is that, when we are operating in a higher frequency, this Z parameter we can derive it with the help of S parameter, but directly for the higher frequency component Z parameter is very difficult to identify. But once this S parameter is known, we can convert S into Z, we can convert S into ABCD, we can convert S into hybrid parameter, we can convert S into admittance parameter. Okay, so as you can see, I have written the potential is equals to impedance into I. Okay, now here I have written which is equals to Z whole into A minus B. A is the incident one and B is the reflected potential. So this is the normalized component I have written. Okay, so this Zi component is normalized written in terms of A and B. So Z whole into A minus B, incident minus reflected, which is equals to more incident potential plus reflected potential. So if you add this, you will get your current, because this is normalized potential relations. Next, if I want to determine A and B, common. So you have to multiply Z into A, Z into B, and take a common of A, take a common of B. If I am taking, I will get mod Z plus unitary matrix into B, then Z minus unitary matrix into A, and take this B component, means this component to the right hand side, you will get B with respect to A. So what is B with respect to A? B is the reflected normalized potential and A is the incident normalized potential. If you form a relation, you can see that B is equals to S into A. So that means I have converted my Z impedance in terms of normalized potential, and that normalized potential impedance is converted into S matrix. So in this line you can see, if I will take this term to right hand side, it will take as an inverse because it is a matrix. So consider this is as X matrix, this is as Y matrix. So if you take X to right hand side, it will become as X inverse. So same inverse I have written, same thing Y I have written into A. So now I have represented B and A, and this is one sort of matrix. Now we have a general equation, B is equals to S parameter into A, because this S parameter forms a relationship between reflected with incident potential. Now if you compare this S is nothing but the combination of this matrix. So here I have written, so S is equals to Z plus unitary matrix inverse into Z minus unitary matrix. So this is my value. Now how to identify these relations? I have converted into S. Now my main target is my S transpose must be equal to S, then only I will say it is called as a reciprocal network. So for that, let us consider this Z plus U as R matrix and Z minus U as Q matrix. Here I have written. So R is equals to Z minus U and Q is equals to Z plus U. So here, if it is a reciprocal network, product of R into Q must be equal to Q into R. So this is I have written, R into Q is equals to Q into R. For a reciprocal network, Z matrix is symmetric in nature. Now I have to resolve this. I need to identify the relation with respect to S and transpose. So how I will going to identify? The simple technique is, both this side I have to multiply the inverse. So here you have seen, here I have multiplied Q inverse and here also Q inverse. So Q inverse into R, then Q inverse, or you can take R also, no problem, anyone. In right hand side also Q inverse, Q into R and Q inverse. Okay, so Q into R, and if you can see that A into A inverse, resultant is 1. So resultant is 1. Similarly, Q inverse into Q, resultant is 1. So what I am getting? The first component Q inverse into R and this R into Q inverse. Okay. Now here, as we know, S transpose. So S is this much. If I will take transpose both the side, so Z minus U transpose first component, then Z plus U inverse transpose is the second component. As you can see here, I have written the Z plus U inverse transpose and Z minus U whole transpose. Now in place of Z minus U, you have to substitute, if it is a reciprocal network, then Z minus U transpose will become Z minus U, and Z plus U transpose, you will get Z plus U. So assuming these two values, substitute in this case, it is Z minus U, Z plus U inverse. It is nothing but S. So this S transpose is equals to S. So we have converted the relation from impedance matrix to the scattering matrix, and then we have formed a relation that S transpose is equals to S. So this is called as a reciprocity theorem, or it is called as a reciprocal property for a microwave network dealing with S parameter. Okay, so this is the simple derivation Only the matrix multiplication and inverse I have took to make you understand, and this is the basic proof for the reciprocal network. So first property is what? If it is perfectly matched, diagonal elements are 0. Diagonal elements are what? Diagonal elements all are reflection coefficient. If all the ports are perfectly matched, means ZL is equals to Z0, the total reflection coefficient of that all port is 0. So diagonal element will be 0. Next, if it is a reciprocal network, your transpose of S matrix must be equal to S. That you have to prove. So this is a simple way to prove the S transpose is equals to S. Then only we will say it is a reciprocal in nature. Otherwise it is not a reciprocal network. Okay. So after that, two more properties are there that I will discuss. Okay. So this is the third property, which is called as unitary property, and it is basically measured for the lossless network. Second one we have identified for the reciprocal network. Now, if it is a lossless in nature, lossless in nature means total input power must be equal to total output power. So that is the first analogy. Second, now which particular port we are going to excite, okay, with respect to whom? Because if we are considering two port network, that which port is excited, that we have to identify. If it is a 4-port network, which port is excited and what are the other port we are going to do, okay. So according to that we have to measure all these parameters. So first analogy is what? If it is a lossless in nature, lossless means input power must be equal to output power. Now let us consider for port 1 is excited. For nth port we are considering. So for nth port, input power and output power I can measure. It is summation 1 to n number of port, summation of an square. Summation of all the input port must be equal to summation of all the output port. Okay, output power. So input power n, if it is a with respect to port 1, if I am measuring, that means a1 square must be equal to b1 square. That means input power and output power will be same. Now this bn I can write for, let us consider for the ith port measurement. Okay, there are n number of port in which we are considering for the ith port. So I have substituted what is bn. Bn is nothing but S is equals to b by a. Okay, so if it is bi and ai, then I can write for the nth port S suffix ni. So S suffix ni is equals to bi by ai. So in place of bi, I can write S ni into ai. So that I have substituted here in place of bi. So S suffix ni into ai mod square, which is equals to an. Now an will become as ai because ith port we are considering. So it will become ai. As you can see, I have written in this equation. So summation of n equals to 1, n number of ports, S suffix ni dot ai whole square is equals to n equals to 1 to n summation ai square. Now here mod of ai square and here mod of ai square is there with the same limitation. It can be cancelled out and you will get the resultant value is 1. So what it is? Summation n equals to 1 to n S ni square 1 is equals to, it is nothing but S ni into complex conjugate of S ni. Then only it will multiply, resultant is mod S ni whole square. Now what it is actually? So this particular relation is equals to 1. But it is with respect to the matrix only. But theoretically, or the how we can analyze all these things. Remember that if we are considering two port network, it is having two rows and two columns. Okay, so according to this principle, either you can take row or either you can take column. Square of each term with respect to the row and square of each term with respect to the column, if you add those components, must be equal to 1, and that is the property of lossless junction. Let me take one example for you so that it will be easy to understand. So let us consider 2-port network, then I will consider 3-port network. 3-port network. Okay. So if it is 2-port network, we are having 4 parameters, S11, S12, S21 and S22. According to this property, either you go for the row or either you go for the column, anyway, any row, any column, but it must be in the same form. Mod of S11 square, mod of S12 square. Okay. Now here nth port is there. Okay. In place of n, substitute 1. In place of n, substitute 1. And if it is 2-port network, your I value will be 1 to 2. Okay. So that means how much I will get? First 1 1, then 1 2. So mod square, and this is mod square if I am going with respect to the row. So this is the first case. So this must be equal to 1. This is with respect to row I am considering. Similarly, S21 square plus S22 square must be also equal to 1. Any row, individual square, add it. If resultant is 1, then you can say it is a lossless network. This is with respect to row I have written. Similarly, if I will write with respect to column, S11 square plus S21 square, it is equals to 1. S12 square plus S22 square is equals to 1. Then it is called as a with respect to column. Okay. So you can verify with respect to row and with respect to the column if it is a 2-port network. Now let me take a 3-port network in which 9 elements will be there. S11, S12, S13, S21, S22, S23, S31, S32 and S33. Okay. Now same thing with respect to row and with respect to column. If you take an individual square and add it, if resultant is 1, then we can say it is called as our lossless network. So if you consider row, row 1, row 2. So if I am taking row 1, mod S11 square plus S12 square plus S13 square is equals to 1 if it is there, that means it is a lossless in network. Similarly, R2 is equals to S21 square plus S22 square plus S23 square is equals to 1. It is not mandatory to calculate all the row. You have to test. First, if you test whether if it is a row is equals to 1 or not. If it is not, then test for column. If in column also if it is not that, then it is considered as a not a lossless network. It is a lossy network. Okay. So for the explanation I am making it R1, R2 and R3. So like this test you can make it. S31 square, S32 square, S33 square is equals to 1. This is with respect to row I have taken. Similarly, column wise also you can take C1 as S11 square plus S21 square plus S31 square is equals to 1. C2 is S12 square plus S22 square plus S32 square is equals to 1. Similarly, column third is S13 square plus S23 square plus S33 square is equals to 1. Any of this combination, if you check if it is equals to 1, that means your network is a lossless network. Okay. So this is the third property. Fourth property comes for phase shift. If you change the port position, suppose this is the port 1 position, this is the port 2 position. If you change this position, your length is going to change. And once the length is going to change, that means your phase component is going to change, because e to the power minus j beta l for the lossless network what we have considered, if you change the position, your phase is going to completely change. That we have to prove. Okay. So the phase shift property and the numericals we are going to discuss in the next class. For the today we'll end up at this time, because time is already over for us. So next class we'll discuss about the phase property and the numericals regarding the scattering parameter. Okay, thank you all.